Hello, and welcome to part 5 of this video playlist about the preparation of alkylarenes. This video is about the alkylation of aryl halides and other substituted arenes, acting either as electrophiles or as nucleophiles. This is a huge area, and I'll limit myself to the most accessible starting materials to show you the basic strategies and their scope. We'll start with the alkylation of stoichiometrically metallated arenes by alkyl halides, sulfonates, and other electrophiles. This will be followed by examples of the reaction of aryl halides with polar organometallics and with alkenes, both with and without transition metal catalysis. Then we'll have a look at the coupling of aryl halides with alkyl electrophiles. And finally, I'll show you examples of the arylation of enolates. The stoichiometric metallation of aryl halides by transmetallation often requires low temperatures because aryl lithium or aryl magnesium halides react with alkyl halides. When butyl lithium is added to an aryl bromide, the aryl lithium and butyl bromide are formed. If the temperature is too high, or if a reactivity-enhancing solvent was chosen, the aryl lithium will be alkylated by butyl bromide. This can be avoided by lowering the temperature or by conducting the reaction in heptane with a small amount of THF only. Aryl Grignard reagents are only weak nucleophiles towards simple alkyl chlorides and can even act as bases and cause dehydrochlorination. Some transition metals do, however, catalyze the alkylation of aryl magnesium halides. Best results were achieved here with 4% of palladium acetate as catalyst. With suitable ligands, even inexpensive iron could be used as catalyst. Much better results can be achieved with alkyl bromides as electrophiles. Both phenyl magnesium bromide and phenyl lithium reacted cleanly with octyl bromide when 3% of copper chloride had been added. Without copper catalysis, the yields were lower. Alkyl fluorides are difficult to prepare, often toxic, and poor electrophiles. And as shown here, alkyl fluorides do not alkylate Grignard reagents well because of their low electrophilicity. Surprisingly, even secondary alkyl halides do react with phenyl magnesium bromide in the presence of iron catalysts. Secondary alkyl halides readily eliminate the hydrogen halide and often yield product mixtures when treated with nucleophiles like amines, alkoxides, or cyanide. In this example, however, the reaction of phenyl magnesium bromide and 5% of iron trichloride with sec-butyl chloride, bromide, and iodide gave high yields of sec-butyl benzene. As an alternative, such reactions can also be catalyzed by cobalt. Here, a secondary alkyl iodide alkylated an aryl magnesium bromide with 5% of a copper diamine complex as catalyst. The electrophilic methylation of aryl Grignard reagents can be achieved with dimethyl sulfate. No catalysis was required in this case, but the yield was only fair. I'll show you now some examples of the reaction of polar organometallics with aryl electrophiles, both with and without transition metal catalysis. Without catalyst, these reactions can be simple aromatic nucleophilic substitutions, or may proceed by intermediate arynes, what can yield mixtures of regioisomers. Here, a benzylic organolithium reagent was generated by direct lithiation with sec-butyl lithium. Arylation with an excess of chlorobenzene without any catalyst gave a low yield of the expected product. With iron catalysis, we see an interesting dependence on the leaving group. Chloride and sulfonates were displaced, preferentially from electron-deficient arenes, while bromides and iodides were mainly reduced. Best results were obtained in mixtures of THF with polar aprotic solvents, for instance N-methylpyrrolidinone. It is assumed that complexes with negative charge at iron are formed, which are sufficiently nucleophilic to insert into carbon-chlorine or carbon-oxygen bonds. This is another example of iron-catalyzed alkylation of an aryl chloride with a Grignard reagent. Electron-deficient aryl halides reacted faster under these conditions than electron-rich aryl halides. No substitution or reduction of the sulfonyl group occurred. Here, a triflate was alkylated with octyl magnesium bromide and catalytic iron. The acetic ester also reacted with the Grignard reagent, but a bit more slowly. The twofold methylation of a dibromocarbazole with methyl magnesium bromide was catalyzed by a nickel complex in this instance. In this example, an aryl bromide reacted smoothly with allyl magnesium chloride and a palladium catalyst. The main product was the allyl arene, and double bond migration occurred to a small extent only. Tert-butyl magnesium chloride can also be used to alkylate aryl bromides. Here, the reaction was catalyzed by a nickel-carbene complex. Organozinc reagents are less nucleophilic and basic than organomagnesium or lithium compounds. With the aid of a palladium catalyst, however, here an aryl bromide was alkylated in high yield with a functionalized organozinc bromide. This reagent was prepared directly from an alkyl bromide, but zinc insertions are more difficult than the preparation of Grignard reagents. Electron withdrawing groups in arenes can promote the displacement of ortho-alkoxy groups. Here, the imine of a 2-methoxybenzaldehyde was treated with an excess of ethyl magnesium bromide and catalytic manganese chloride. Hydrolysis then yielded the orthoethylated benzaldehyde. Without protection as imine, the formyl group would probably have reacted with the Grignard reagent to a secondary alcohol. Even unprotected phenols undergo similar reactions. In the second equation on this slide, a larger excess of Grignard reagent and 10% of copper chloride brought about displacement of bromide from the amine of 2-bromo-5-hydroxybenzaldehyde. Fluoride is a good leaving group for aromatic nucleophilic substitutions. These reactions are not usually catalyzed by transition metals because these metals cannot insert into the strong carbon-fluorine bond. Here, one fluoride was displaced selectively from a trifluorophenyl group with an excess of methyl magnesium chloride. This here is a rare example of the use of a transition metal complex to catalyze the substitution of aromatic fluoride. Again, only fluoride ortho to the activating group was displaced, here by benzyl zinc chloride. Boranes are weak carbon nucleophiles and require catalysis to react with aryl halides. Here, a palladium complex mediated the coupling of a phenethylborane with 4-bromoacetophenone. Like in the previous example, no addition to the carbonyl group occurred. Many reactions of this type have been reported, and I won't show you more because boranes are expensive reagents and only rarely applicable to large-scale preparations. Here, the borane was synthesized from a Grignard reagent, but as I've shown you, Grignard reagents can also alkylate aryl bromides directly, even in the presence of carbonyl groups. As an alternative to triflates or tosylates, carbamates can be used as electrophiles in alkylation reactions. In this example, such a displacement was catalyzed by an iron-carbene complex. Aerophosphonium salts are another type of electrophilic arylating reagent. Here, a pyridyl phosphonium triflate reacted with cyclobutyl zinc chloride and 5% of a cobalt complex to the cyclobutyl pyridine. As a side reaction, debromination of a bromophenyl group occurred to a small extent. The required pyridyl phosphonium triflate was prepared by oxidative carbon-phosphorus bond formation with triflic anhydride. The latter was reduced to a sulfonate. Few examples have been reported of the substitution of carboxyl groups. Acyl anions are energy-rich, difficult to generate, and thus poor leaving groups. Here, N-phenylphthalimide reacted with an excess of diethyl zinc and one equivalent of a nickel complex to 2-ethylbenzanilide. The large amount of nickel was required because the released carbon monoxide probably deactivated the nickel catalyst. I'll show you now some examples of the arylation of alkenes with aryl electrophiles. Depending on the catalyst and the conditions, these reactions can yield alkylarenes or vinylarenes. Unlike most acid-catalyzed Friedel-Crafts alkylations with alkenes, here mostly linear products are formed. The reaction of olefins with unsubstituted arenes is discussed in part 2 of this video playlist. In this example, the coupling of bromobenzene with styrene was catalyzed with 2% of a bulky palladium complex. Under alkaline conditions in sec-butanol, a high yield of 1,2-diphenylethane resulted. Stilbene and 1,1-diphenylethane were formed as byproducts, especially in propanol as solvent. With a simple, unactivated terminal alkene, an aryl triflate, an excess of deuterated sodium isopropoxide, and nickel catalysis, mainly a branched alkylarene was obtained. Thus, the outcome of these reactions is difficult to predict correctly. Here, with a less bulky nickel catalyst, an internal alkene isomerized to a terminal alkene and was then arylated at the less substituted carbon atom with an aryl iodide. I'll show you now some examples of the reductive coupling of aryl halides with alkyl halides. These reactions can proceed by metallation of one of the two halides or via radicals. Important side products are symmetric dimers, and the yields of cross-coupled products are sometimes low. This here is one possible mechanism with free radicals as intermediates. In part 4 of this video playlist, there are examples of the alkylation of unsubstituted arenes with alkyl radicals. In this example, bromobenzene was coupled with bromobutane just by stirring with metallic sodium for 2 days. In this more recent example, 2 bromides were coupled with zinc and 5% of a nickel-amidine complex. No displacement of fluoride occurred. Similarly, with 2 equivalents of manganese and a nickel catalyst, here an aryl bromide was coupled with a secondary tosylate. Even aryl and alkyl chlorides can be coupled, here again with manganese as reducing agent and 20% of a nickel catalyst. Aryl iodides and alpha-bromo ethers are particularly reactive. These here are optimized conditions for the coupling of aceto-bromoglucose with an aryl iodide. In this example, diphenyl ether was first converted into a sulfonium salt and then coupled with a secondary alkyl iodide. The alkylation was mediated by an excess of zinc and catalyzed with a palladium complex. Similar reactions can be performed with aryl iodides and ketones. In this example, no metal, but a slight excess of butyl lithium was used as metallating reagent. Interestingly, no addition of butyl lithium to the ketone occurred, and only 1 iodide of the arene was substituted. A primary alkyl chloride remained unchanged. Here, a cyclopentyl radical, or cyclopentyl zinc, was generated from an N-hydroxy-phthalimide ester. Nickel-catalyzed coupling with an aryl bromide gave the cyclopentyl arene, along with a small amount of the reduced arene. Similarly, here, a primary alkyl radical was generated from an acid anhydride and then coupled with an aryl iodide. I'll show you now some examples of the electrophilic arylation of ketone and other enolates. Here, because the starting aryl chloride was unreactive, catalysis with a bulky palladium complex was necessary. The ketone enolate was generated from cyclohexanone and sodium tert butoxide. This is an intramolecular palladium-catalyzed arylation of a cyclohexanone with an aryl bromide. With 10% of proline and potassium phosphate as base, the cyclization proceeded with high enantioselectivity. 1,3-diketones are quite acidic, and their enolates therefore less nucleophilic than simple ketone enolates. Nevertheless, with a large excess of acetyl-acetone as solvent, sodium hydride, and 6% of copper bromide as catalyst, the aromatic substitution proceeded as expected. Instead of copper, also palladium can catalyze such reactions. 1,3-diketones and beta-keto esters are readily cleaved by strong nucleophiles, and in this example, the excess of base cleaved off the acetyl group from the initially formed arylated ketoester. Ester enolates are similarly nucleophilic as ketone enolates and can also be arylated with aryl bromides. Here, the reaction was again catalyzed with palladium. In this example, a hydantoin enolate was coupled with an aryl chloride. A bulky palladium complex was required to cleave the strong carbon-chlorine bond. Aliphatic nitriles can be deprotonated with strong bases and then arylated with aryl fluorides without any transition metal catalysis. Another good leaving group for aromatic nucleophilic substitutions is nitrite. Here, nitrotoluene was coupled with propiophenone with the aid of a palladium catalyst. Certain compounds can be metallated at a more distant site from a carbonyl group by chelate formation. These sites may be less acidic than the protons alpha to the carbonyl group if we measure their equilibrium acidities, but will be metallated anyway because of the sterical requirements of the chelate. And many transition metals form strong bonds to carbon that are barely polarized and resistant to hydrolysis. In this example, an imide formed a nickel chelate by gamma metallation of a hexanol group. Arylation with an aryl iodide then yielded the observed product. In this example, a palladium chelate formed by gamma metallation of an amine reacted with an aryl iodide to the gamma aryl amine. The chelating ligand was formed by condensing the ketone with glycine. Palladium had to be reoxidized with silver trifluoroacetate. One potential problem of these reactions is that the product can be more reactive than the starting material, and some optimization may be required to avoid multiple arylations. Here, an oxime was gamma palladated and then coupled with an aryl iodide. Also, simple alkylamines can form chelates and be metallated at a remote position. In this example, a cyclopropylmethylamine was arylated enantioselectively with the aid of a chiral acetamide and catalytic palladium trifluoroacetate. Silver oxide reoxidized palladium to palladium-2. This here is a reaction that I optimized some years ago. Anilines can be converted into aryl propanals directly in a one-pot procedure by diazotization in the presence of allyl alcohol and catalytic palladium chloride. No isolation of the diazonium salt and no expensive reagents or ligands were required. It was important to make sure that the palladium chloride was completely dissolved in acetonitrile, what can take several hours of stirring, depending on the particle size. Reactions with isolated diazonium salts are easier to perform than one-pot reactions, like the previous one, and most diazonium tetrafluoroborates are thermally stable. Here, such an isolated diazonium tetrafluoroborate arylated an enol acetate. The reaction proceeded in aqueous acetonitrile under slightly alkaline conditions without any transition metal catalyst. This reaction is related to the Gomberg-Bachmann synthesis of biaryls and proceeds by base-induced formation of a diazoanhydride. These compounds can fragment into a relatively stable diazotate radical and an aryl radical. The latter then starts a radical chain reaction, where the addition product of the aryl radical to the enol acetate is oxidized by the diazonium salt. The reduced diazonium radical fragments into nitrogen and the aryl radical. Intermediate arynes can also be alkylated. Here, benzene was generated from a triflate in the presence of triethyl phosphite and methyl acrylate. The main product was an aryl propionic ester. Let's check some potential side reactions. Very common is the reduction of aryl electrophiles by organometallics. Alkyl magnesium halides are good hydride donors and can reduce aryl halides by the mechanism sketched here. Organolithium compounds are usually more nucleophilic and less prone to hydride transfer. Such reductions can also proceed by single electron transfer and intermediate radicals. This here is a typical example where most of the product was the reduced arene. With iron catalysts, aryl bromides and iodides are also preferentially reduced. Better results can sometimes be obtained with aryl chlorides or sulfonates. Here are some more examples, which you can also find in the description of this video. Under the Posts tab of my channel, there is a copy of the slides. This was the last video of this playlist, and I hope there was something useful for you. See you all next time.